more than 24 billion kilometers from Earth, far beyond the outer boundary of the solar wind. Voyager 1 drifts through absolute dark. At this immense distance, the sun is no longer a warm, brilliant disk in the sky, but a blinding tiny point of white light, completely incapable of warming the metallic hull of the spacecraft. Surrounding the probe is the deep background of interstellar space, a realm where ambient temperatures drop to less than 3 degrees above absolute zero. Under these extreme cosmic conditions, heat is not merely a comfort or an operational convenience, it is the fundamental currency of physical survival. Without a continuous internal heat source, delicate digital electronics would freeze into inert silence. Structural metals would warp and stress under extreme thermal contraction, and the liquid hydrazine propellant used for attitude control would turn to solid ice within seconds, leaving the spacecraft tumbling helplessly and blindly through the interstellar void. Yet, against every theoretical expectation of mid-20th century aerospace engineering, Voyager 1 continues to transmit clear, structured radio signals across the cosmic expanse. Its half-century of survival is not an accident of good fortune, but a masterclass in thermodynamic engineering, solid-state nuclear physics, and algorithmic triage that has allowed a machine constructed in 1977 to outlive its original human creators in the coldest, harshest environment in the galaxy. If you enjoy deep, immersive explorations of real astrophysics and the extraordinary engineering that expands our horizon into the cosmos, please consider liking this video and subscribing to the channel. Your support helps us create more long-form documentaries that uncover the quiet mechanics of the universe. To understand how a human-made machine survives in the vastness of deep space, one must first dismantle the familiar terrestrial intuition of what cold actually is. On Earth, human beings and mechanical systems experience cold predominantly through thermal conduction and atmospheric convection. When cold air flows across exposed skin, metallic machinery, or building structures, trillions of moving atmospheric gas molecules collide continuously with the surface matter, rapidly absorbing kinetic vibrational energy and carrying it away into the surrounding fluid. On Earth, the dense gaseous atmosphere acts as an active, aggressive thermal exchange medium, stripping heat away from warm objects with relentless physical efficiency. In interstellar space, however, atmospheric density drops to absolute near zero. The medium surrounding Voyager 1 consists of an astonishingly sparse, diffuse plasma containing fewer than 1 hydrogen atom per cubic centimeter. In such a profound physical vacuum, thermal conduction and atmospheric convection effectively cease to exist. A warm mechanical object placed in this interstellar vacuum does not lose its internal heat to the surrounding space through direct physical contact, simply because there are virtually no surrounding gas particles available to collide with its outer hull. Instead, thermal dissipation in the absolute vacuum of deep space is governed entirely by the laws of thermal radiation. Every physical object possessing a temperature above absolute zero continuously radiates energy outward into space in the form of electromagnetic waves, predominantly within the infrared spectrum. This fundamental radiative process is quantified mathematically by the Stefan-Boltzmann law, which dictates that the total radiant energy emitted per unit surface area is directly proportional to the fourth power of the object's absolute temperature in Kelvin, multiplied by its material surface emissivity and the fundamental Stefan-Boltzmann constant. Because of this steep fourth power mathematical relationship, a warm physical object radiates heat away with extreme rapidity at elevated temperatures, but as its physical temperature drops, its rate of energy emission slows down exponentially. However, in the vast interstellar expanse beyond the boundary of our solar system, the external cosmic environment offers virtually no incoming radiant thermal energy to counterbalance this continuous loss. The The cosmic microwave background radiation, the faint thermal echo left behind by the Big Bang, floats at an average temperature of approximately 2.7 Kelvin. For Voyager 1, the surrounding interstellar sky acts as a perpetual thermal sink, an infinite black radiator that absorbs every single infrared photon emitted by the spacecraft while offering almost zero incoming thermal photons in return. This thermal reality introduces a fundamental physical distinction between kinetic temperature and total heat capacity that is critical to understanding deep space survival. In thermodynamics, temperature is a microscopic measure of the average kinetic energy of individual particles within a given system, whereas heat capacity represents the total aggregate thermal energy contained within a bulk mass. In the local interstellar medium, individual gas ions and free electrons may possess kinetic energies corresponding to microscopic temperatures of several thousand degrees Celsius. However, because the particle density is so astonishingly low, a minute fraction of an atom per cubic centimeter, the total heat content of the interstellar plasma is virtually zero. When Voyager 1 travels through this medium, the occasional high-velocity ion striking its outer hull transfers an infinitesimal amount of kinetic energy, far too small to influence the spacecraft's bulk physical temperature. The probe is effectively suspended in a thermal void where the density of physical matter is completely insufficient to conduct heat either into or out of the spacecraft structure. Consequently, Voyager 1's physical temperature is determined entirely by the internal balance of energy generation and radiative photon emission. Every single joule of thermal energy residing within the spacecraft's structural aluminum chassis, its electronic circuit boards, and its titanium propellant tanks originated as internal nuclear decay. As this thermal heat diffuses through the probe's metal frame, it eventually reaches the outer structural boundaries, where it is converted into infrared photons that launch into the void at the speed of light. Because the surrounding cosmic background radiation is so profoundly cold, these outgoing infrared photons never return, and virtually no incoming thermal photons arrive from distant stars to replenish the continuous energy loss. The interstellar environment does not press against the spacecraft like a freezing winter wind. Rather, it surrounds the probe like an infinite silent vacuum pump, continuously drawing away its internal heat energy photon by photon. The thermal landscape changes subtly but significantly as a spacecraft crosses from the heliosphere into the surrounding interstellar medium. Inside the heliosphere, the Sun emits a continuous, expanding bubble of ionized solar plasma known as the solar wind. Although the solar wind is extremely diffuse compared to Earth's atmosphere, it carries a dynamic magnetic field and energetic ions that maintain a relatively high local plasma pressure around the inner planets. Furthermore, while solar irradiance drops rapidly with the inverse square of distance, even at the remote orbits of Neptune or Pluto, solar photons still impart a measurable, albeit minor, radiative thermal energy input to exposed surfaces facing the Sun. When Voyager 1 crossed the heliopause, the sharp magneto-hydrodynamic boundary where the outward pressure of the solar wind is balanced by the inward pressure of the advancing interstellar cloud, it left the Sun's protective thermal umbrella entirely. Outside the heliopause, the local density of interstellar plasma increases by more than an order of magnitude, transitioning from thin, solar-dominated plasma to the denser, cooler gas of the local interstellar cloud. While this increased density is still vastly less than any physical laboratory vacuum achievable on Earth, it alters the optical and electromagnetic environment surrounding the probe. The spacecraft is no longer illuminated by a dominant central stellar source. It is exposed equally on all sides to the cold, isotropic radiation field of the galaxy. To analyze this photon emission mechanics further, consider the Planck radiation distribution across infrared wavelengths. At internal chassis temperatures of roughly -20 degrees Celsius, 253 Kelvin, the peak wavelength of electromagnetic energy emitted by Voyager 1's outer skin occurs in the far infrared spectrum at approximately 11.5 micrometers. The thermal photons flowing outward from the Kapton insulation blankets carry away energy at a precise rate governed by the material's surface emissivity coefficient of roughly 0.8. If an instrument compartment's internal power dissipation drops by just 10 watts, the local skin temperature must plunge by several Kelvin before the radiative photon flux drops sufficiently to re-establish steady-state thermodynamic equilibrium. Furthermore, the geometry of heat loss in a multibody spacecraft introduces complex radiative view factors. Individual structural components do not radiate exclusively into the cold cosmic void. They also radiate toward neighboring spacecraft structures. The large 3.7-meter high-gain parabolic antenna dish acts as a massive thermal reflector, shielding the top face of the decagonal equipment bus while reflecting a fraction of the bus's emitted infrared radiation back toward the central structure. Engineers had to map these internal geometric view factors using complex ray tracing algorithms to ensure that radiative heat bouncing between adjacent bus panels did not create localized thermal hotspots or accelerate heat leakage from shadowed compartments. In addition to structural view factors, the spectral absorptivity and emissivity ratios of exterior coatings play a definitive role in passive thermal management. Spacecraft thermal control engineers classify surfaces by their solar absorptivity to thermal emissivity ratio. On the inner planets, low absorptivity to emissivity coatings reflect bright visible sunlight while radiating thermal heat effectively into space in the interstellar deep freeze. However, solar absorptivity is entirely irrelevant because solar illumination is negligible. The thermal equilibrium of Voyager 1 is dominated exclusively by far-infrared emissivity. Every exposed surface from the carbon black painted Kapton blankets to the bare aluminum structural brackets was chosen based on its ability to minimize unwanted radiative leakage into the dark sky. Finally, the physical mechanism of photon momentum escape introduces a subtle mechanical force linked directly to thermal radiation. As infrared photons leave the spacecraft skin, they carry away momentum defined by Planck's equation. If one side of the spacecraft radiates slightly more thermal energy than the opposite side, this asymmetric photon emission generates an infinitesimal recoil thrust, a phenomenon known as the thermal recoil force, or pioneer effect. While this thermal force is far too tiny to alter Voyager 1's physical temperature, it illustrates the profound physical truth of deep space. Thermodynamics, every single watt of heat escaping into the cosmic void carries physical momentum, mass energy, and thermodynamic entropy away from the probe. Evaluating the thermodynamic state of an interstellar probe requires analyzing the microscopic relaxation times of atomic energy states. Within solid structural metals, thermal energy is distributed among lattice vibrational modes known as phonons. In a terrestrial atmosphere, gas collisions rapidly equilibrate surface lattice phonons with atmospheric molecular motion. In the interstellar vacuum, however, surface phonons can decay only by spontaneously emitting infrared photons into space or by scattering internally against lattice impurities and structural grain boundaries. This fundamental quantum mechanical constraint dictates that heat transport within the spacecraft frame is dominated entirely by internal phonon-phonon scattering across metal crystal domains, while heat loss to the universe is strictly mediated by spontaneous photon emission. Furthermore, the quantum mechanical nature of infrared photon emission at ultra-low temperatures involves subtle microscale thermal dynamics. As an aluminum equipment chassis cools from room temperature down to -30 degrees Celsius, the peak vibrational frequency of its crystal lattice shifts toward the lower phonon energies. The spectral radiance curve broadens in accordance with the Planck distribution law, shifting the emitted thermal photon spectrum into the far-infrared regime. Because the surrounding cosmic background offers no offsetting photon flux at these wavelengths, every emitted phonon-converted photon represents a permanent loss of internal physical heat that can never be recovered through external thermal absorption. A rigorous examination of the cosmic microwave background spectral energy density highlights why interstellar radiative heat loss is so unyielding. The CMB blackbody curve peaks at a wavelength of approximately 1.9 millimeters, corresponding to a photon density of roughly 411 photons per cubic centimeter. However, the energy carried by these microwave photons is on the order of microelectron volts, far too feeble to excite vibrational phonon modes in aluminum or titanium crystal lattices. Consequently, while Voyager 1 is bathed in a continuous bath of relic Big Bang photons, these low-energy photons pass through or reflect off the metallized hull without transferring any meaningful kinetic warmth to the cold spacecraft structure. The cognitive shift in understanding Voyager's survival lies in recognizing that cold in deep space is not an aggressive atmospheric force attacking the hull, but an absolute silence, a thermodynamic void into which every joule of energy endlessly leaks. The spacecraft is not fighting an invading chill. It is fighting the continuous loss of its own internal thermal identity. If a spacecraft loses its internal heat generation, it does not freeze because space chills it. It freezes because it radiates its own vitality away into an infinite sink that never fills. Maintaining internal thermal integrity across decades of deep space transit requires a precise physical balance where every single incoming and outgoing photon must be accounted for within a strict energy budget. If the rate of internal heat generation drops even slightly, the spacecraft's physical temperature must decay until a new, lower radiative equilibrium is established. If that equilibrium temperature falls below the physical thresholds required for structural materials and fluid propellants, the machine ceases to function. Voyager 1's survival is therefore not a story of passive resistance against an external freeze, but an active continuous internal balancing act governed by the uncompromising laws of radiation thermodynamics. Because solar radiation decreases with the inverse square of distance from the sun, photovoltaic solar panels become completely useless long before a spacecraft reaches the outer boundaries of the solar system. At the distance of Earth, 1 astronomical unit from the sun, solar panels receive approximately 1,366 watts of solar power per square meter of exposed area. By the time a planetary probe reaches Saturn at 10 astronomical units, that incoming solar energy flux drops to a mere 1% of its terrestrial value. Out at Voyager 1's current interstellar position, more than 160 astronomical units from the sun's solar irradiance has plummeted by a mathematical factor of over 25,000. At this immense cosmic distance, a solar panel array the size of an entire football field would generate barely enough electrical current to illuminate a single household light bulb, while providing zero meaningful thermal warmth to the spacecraft chassis. To survive and operate in this permanent cosmic shadow, Voyager 1 relies entirely on solid-state nuclear physics. Its operational power and physical heat do not originate from chemical combustion, electrical storage batteries, or collected stellar light, but from the spontaneous, relentless disintegration of artificial atomic nuclei, housed within 3 multi-hundred-watt radioisotope thermoelectric generators, commonly known as RTGs, mounted together on a dedicated structural boom extending several meters outward from the spacecraft's main body. These 3 cylindrical generators serve as the dual heart and nuclear furnace of Voyager 1, providing the physical energy that has sustained the probe for nearly half a century. At the microscopic core of each RTG lies a fuel supply composed of plutonium-238 oxide. Plutonium-238 is a synthetic radioisotope manufactured in specialized terrestrial nuclear reactors by bombarding Neptunium-237 targets with thermal neutrons. Unlike plutonium-239, which is utilized in nuclear weapons and readily undergoes induced nuclear fission, plutonium-238 is an intense, non-fissile alpha emitter possessing a physical half-life of 87.7 years. This specific nuclear half-life represents an extraordinary sweet spot in nuclear physics. For long-duration deep space missions, it is short enough to release thermal energy at a high power density per unit mass, yet long enough to maintain steady, highly predictable heat generation across multi-decade operational lifetimes. As unstable plutonium-238 nuclei spontaneously decay, each nucleus ejects an energetic alpha particle consisting of 2 protons and 2 neutrons tightly bound together as a helium-4 nucleus with a discrete kinetic energy of approximately 5.5 megaelectronvolts. When these high-velocity alpha particles are emitted inside the dense ceramic matrix of the plutonium dioxide fuel pellets, they cannot travel more than a few micrometers before colliding violently with neighboring plutonium and oxygen atoms. Through these microscopic atomic collisions, the kinetic energy of the ejected alpha particles is instantly thermalized, converting nuclear mass energy into atomic vibrational kinetic energy, raw thermal heat. This energy release is so intense that the fuel pellets naturally glow white hot, reaching internal temperatures exceeding 1000 degrees Celsius purely through their own nuclear self-heating. The structural containment of this nuclear heat source is engineered with extreme mechanical safeguards to prevent radiological release under any plausible failure scenario. The plutonium fuel is pressed into dense, highly stable ceramic spheres of plutonium dioxide. Ceramic materials are selected because they possess exceptionally high melting points and are chemically inert, preventing the fuel from reacting with atmospheric gases or dissolving in liquids if exposed to terrestrial environments. Each ceramic fuel sphere is individually encased within a protective shell of iridium metal, an element belonging to the platinum group that boasts an extraordinary melting point of over 2400 degrees Celsius, alongside extreme resistance to oxidation and chemical corrosion. These iridium-clad fuel capsules are further contained within high-strength graphite impact shells, which are then enclosed inside a heavy graphite heat shield assembly. Graphite is chosen for its unique thermomechanical properties. Its structural strength actually increases at elevated temperatures, and it sublimates rather than melts under extreme thermal shock. This multi-layered graphite assembly was designed to withstand the violent aerodynamic heating and shock forces of an accidental high-velocity atmospheric re-entry during launch, as well as high-impact collisions with terrestrial rock. This nuclear heat source operates entirely passively. It contains no moving mechanical parts, no liquid coolants, no control valves, and no electronic feedback loops. It is an uninterruptible nuclear furnace, driven directly by the quantum mechanical decay rates of atomic nuclei. The transformation of this intense nuclear thermal energy into usable electricity is accomplished through the solid-state thermoelectric effect, specifically utilizing the Seebeck effect discovered in 1821. Arranged radially around the central graphite heat source inside each RTG casing are arrays of solid-state semiconductor thermocouples composed of a silicon-germanium alloy. A thermocouple consists of 2 dissimilar semiconductor materials, one p-type and one n-type joined together at a hot junction, exposed to the central nuclear core, and a cold junction tied to exterior radiator fins facing the cold vacuum of space. When a large temperature differential is maintained across the length of the semiconductor material, electrons and electron holes diffuse away from the hot junction toward the cold junction, generating a continuous direct current electrical voltage gradient across the circuit. Examining the solid-state physics of the Seebeck effect reveals why silicon germanium was selected over other thermoelectric materials such as lead telluride or bismuth telluride. Silicon germanium alloys possess high electrical conductivity combined with relatively low thermal conductivity at elevated temperatures, allowing the thermocouple legs to sustain a sharp thermal gradient without rapidly conducting all the core heat directly to the exterior radiator. The open circuit voltage produced by each individual unicouple is proportional to the Seebeck coefficient multiplied by the temperature gradient. By connecting 312 individual silicon germanium unicouples in a series parallel electrical network inside each RTG, the generator produces a stable 30-volt direct current bus voltage suitable for spacecraft power distribution. Furthermore, helium gas buildup within the iridium fuel capsules presents an interesting long-term fluid containment dynamic, because every alpha particle ejected during plutonium-238 decay eventually captures 2 free electrons to become a stable neutral helium-4 atom. The nuclear decay process continuously generates helium gas inside the sealed iridium shells. Over 50 years of operation, thousands of litres of helium gas at standard pressure are produced within the fuel capsules to prevent catastrophic pressure accumulation from rupturing the iridium containment. The fuel shells incorporate microscopic porous iridium vents that allow helium gas to diffuse slowly out into space while permanently trapping all radioactive plutonium ceramic solids inside. The thermodynamic geometry of the RTG housing also deserves detailed examination. Each generator body is surrounded by outer aluminum radiator fins that extend radially into the vacuum. These fins are coated with high emissivity ceramic paint to maximize infrared photon emission toward the cold sky. By maintaining the outer radiator fins at roughly 150 to 200 degrees Celsius, while the inner hot junction sits at 1000 degrees Celsius, the RTG establishes a stable thermal gradient across the silicon-germanium thermocouple legs. This steady heat flow guarantees both continuous electrical power generation and a predictable directional radiant heat output. A detailed analysis of thermal energy transport within the RTG assembly illustrates the cascading steps of nuclear energy conversion. The primary energy source, nuclear mass deficit, converted to alpha, particle kinetic energy, thermalizes within the ceramic fuel lattice at an efficiency approaching 100%. Next, this vibrational kinetic energy conducts radially outward through the iridium shell, across an argon-helium conductive gas gap, and into the graphite impact sleeve. From the outer graphite heat shield, heat transfers via both conduction and high-temperature infrared radiation across a narrow vacuum gap to the hot junction receiver shoes of the silicon-germanium unicouples. Every thermal interface was calculated to maintain the hot junction at its optimal operating temperature of 1000 degrees Celsius, while shedding non-converted waste heat into space. Furthermore, the solid-state physics of electron diffusion within the silicon-germanium p-n junctions reveals a fascinating thermodynamic self-regulation mechanism. As thermal heat flows across the unicouple leg from the hot junction to the cold junction, the thermal gradient maintains a continuous diffusion gradient of majority charge carriers. The movement of these electrons and holes creates an internal electric field that opposes further charge buildup, establishing steady-state voltage potential. This thermoelectric generation process acts as a continuous solid-state heat engine, extracting work in the form of electrical current while allowing 93% of the core thermal flux to pass through as structural waste heat that shields the spacecraft from freezing. At the microscopic scale of the ceramic matrix, accumulation of helium decay, daughter products also create subtle lattice strain over multi-decade lifespans. As alpha particles capture electrons to form neutral helium atoms within the plutonium dioxide crystal structure, tiny gas bubbles accumulate along grain boundaries within the ceramic pellet. Nuclear ceramic engineers modeled this microbubble growth to ensure that local lattice expansion would not cause microcracking or structural fragmentation of the fuel pellets under continuous thermal shock, preserving the uniform geometry of the central thermal source. The cognitive shift in analyzing the RTG lies in recognizing its fundamental energy balance. It is primarily a nuclear thermal furnace, and only secondarily an electrical generator. The thermoelectric conversion efficiency of silicon-germanium thermocouples is remarkably low. Only roughly 6 to 7% of the thermal heat produced by the plutonium decay is converted into electrical current. At launch in 1977, Voyager 1's 3 RTGs generated approximately 4,700 watts of raw nuclear heat, yielding just 470 watts of electrical power. The remaining 93% of the energy, over 4,000 watts, was shed directly as thermal heat. Far from being a wasteful byproduct, this massive surplus of nuclear thermal energy became the single most critical asset for the spacecraft's physical survival. The RTGs act as a continuous heat engine whose thermal plume is carefully harvested to keep Voyager 1's structural frame and internal systems from freezing solid in the cosmic void. While the 3 RTGs generate thousands of watts of thermal energy, that heat is localized on a structural boom extending several meters outward from the main body of the spacecraft. This physical separation was necessary during spacecraft design to protect sensitive scientific instruments and digital computing circuits from the low-level flux of gamma rays and neutrons emitted by the nuclear fuel. However, this separation created a major thermal engineering challenge: how to transport thermal energy from the isolated RTG boom to the central structural chassis of Voyager 1, where liquid propellants and sensitive electronics reside. The central structural backbone of Voyager 1 is a 10-sided hollow aluminum housing known as the decagonal bus. Inside the 10 individual bays of this bus are the primary electronic subsystems, the command computers, radio transmitters, data storage units, attitude control electronics, and power distribution hardware. Positioned directly within the central cavity of this decagonal frame sits the spacecraft's primary propulsion system, a spherical titanium fuel tank containing liquid hydrazine monopropellant, connected via a network of thin-walled titanium pipes to 16 small attitude control thrusters mounted on external corners of the chassis. Among all the subsystems on board Voyager 1, none is more thermally vulnerable to the extreme cold of interstellar space than this hydrazine propulsion system. Voyager 1 does not use large rocket engines for acceleration in deep space, but it relies continuously on its 16 small hydrazine thrusters to execute microsecond pulses. These pulses generate tiny torques that adjust the orientation of the probe, keeping its 3.7-meter high-gain parabolic antenna pointed toward Earth with an accuracy of better than a fraction of a degree. If attitude control is lost, the antenna will drift off target within hours, severing the ultra-narrow radio link with NASA's deep space network and ending the mission instantly and permanently. The physical threat to this system lies in the molecular phase change properties of liquid hydrazine. Hydrazine is a hypergolic chemical compound composed of nitrogen and hydrogen that freezes at approximately 2 degrees Celsius, just slightly above the freezing point of pure water. If the temperature of the central titanium fuel tank or any of the narrow feed lines drops below 2 degrees Celsius, the liquid hydrazine inside begins to crystallize and freeze solid. As hydrazine solidifies, it undergoes thermal contraction, forming rigid ice plugs that block propellant flow to the thrusters. Worse still, if frozen hydrazine inside a closed pipe is subsequently warmed by adjacent electronics, the thermal expansion of the melting liquid can generate immense hydrostatic pressures that burst the thin-walled titanium tubing. A single, ruptured fuel pipe would vent the entire propellant supply into space, leaving Voyager 1 tumbling helplessly in the void. To prevent the hydrazine lines from freezing, aerospace engineers designed a multi-layered thermal control network combining passive thermal conduction paths with active electrical heating elements. The central spherical fuel tank is thermally coupled to the aluminum structural frame of the decagonal bus using high-conductivity aluminum mounting rings and thermal straps. As electronic components inside the equipment bays consume electrical power, their waste heat conducts directly into the aluminum chassis plates, creating a warm thermal reservoir surrounding the central fuel tank. This conductive loop keeps the bulk hydrazine liquid inside the main tank at a stable, comfortable temperature well above its freezing threshold. However, the thin titanium fuel pipes leading from the central tank out to the external thruster clusters extend beyond the protective enclosure of the main chassis, exposing them directly to radiative heat loss into cold space. Titanium is chosen for propellant lines because of its high strength-to-weight ratio and chemical compatibility with hydrazine, but it possesses relatively low thermal conductivity compared to aluminum or copper. To maintain propellant flow along these exposed pathways, engineers wrapped delicate electrical resistance heater strips directly around the titanium pipes. These heaters draw electrical current from the main power bus, converting electrical energy back into direct thermal heat, applied continuously along the outer walls of the propellant lines. In localized critical areas where electrical wiring would be too complex, or where electrical power failures could prove fatal, Voyager 1 incorporates specialized radioisotope heater units, or RHUs. An RHU is a miniaturized thermal capsule containing a tiny pellet of plutonium-238 oxide that generates approximately 1 watt of pure thermal heat continuously through alpha decay. Unlike the large RTGs on the external boom, an RHU contains no thermocouples and generates no electricity. It is a purely thermal hand warmer encased in a small iridium shell and graphite heat shield weighing just 40 grams. 9 of these tiny nuclear heaters were strategically installed throughout Voyager 1 structure, positioned directly adjacent to critical thruster valve assemblies, mechanical actuators, and sun sensor brackets. Because an RHU operates independently of the spacecraft's electrical bus, its thermal output cannot be disrupted by electrical short circuits, computer resets, or voltage drops. It provides a permanent, uninterruptible thermal floor that guarantees local structural temperatures will remain above freezing regardless of the spacecraft's electrical state. To understand the fluid mechanics of hydrazine under low-gravity thermal management, consider the role of the internal elastomeric bladder inside the fuel tank. The spherical titanium tank contains a flexible rubber bladder that separates the liquid hydrazine from pressurizing nitrogen gas. Under microgravity conditions, surface tension forces cause liquid hydrazine to wet the inner tank walls, while the nitrogen gas exerts constant pressure against the bladder to force liquid propellant into the outlet manifold. If thermal gradients across the tank wall create localized cold spots below 2 degrees Celsius, hydrazine ice crystals can nucleate along the inner titanium surface, sticking to the tank wall and restricting bladder movement. Furthermore, thermal conduction along the electrical wiring harnesses that connect external thrusters to internal drive electronics introduces a secondary heat leakage path. Copper wires possess high electrical conductivity, which inherently correlates with high thermal conductivity according to the Wiedemann-Franz law. Heat from the internal bus bays conducts outward along the copper conductor strands toward the thruster solenoids. Engineers had to carefully optimize wire gauge and sleeve insulation to balance electrical resistance against parasitic thermal conduction, ensuring that wiring trunks did not bleed critical internal heat into the cold thruster mounts. Analyzing the thermal gradient along the thruster feed lines reveals an elegant application of conductive finite element design. The titanium feed tubes feature thin wall thicknesses of less than 0.5 millimeters, which minimizes the physical cross-sectional area available for thermal conduction outward toward the cold thruster pods. By combining low-conduction titanium tubing with strategic aluminum heat-spreading wraps and localized electrical heater strips, engineers created a uniform thermal profile along the entire 3-meter propellant line network. This thermal profile prevents localized freezing spots while consuming fewer than 5 watts of total electrical heating power across the entire propulsion system. Mathematical modeling of thermal diffusion across the decagonal bus structural ring highlights how heat spreads through aluminum structural members. Aluminum alloy 6261T6 features a thermal conductivity of approximately 167 watts per meter Kelvin. Heat generated by high-power transmitter amplifiers in Bay 1 travels rapidly through the circumferential mounting ring, elevating the temperature of adjacent Bay 2 and Bay 10. This structural heat sharing creates a warm ring bus surrounding the central hydrazine tank cavity, insulating the fuel supply against asymmetric radiative cooling. The mechanical strain induced by repeated thermal expansion and contraction cycles on the titanium fuel line brackets requires specialized stress analysis. As the spacecraft rotates or shifts power states, localized temperatures along the lines fluctuate by several degrees, Because titanium alloy T6Al4V has a yield strength exceeding 800 megapascals at cryogenic temperatures, the tubing easily withstands cyclic thermal stresses without microcracking, preserving fluid tight integrity over 5 decades of microgravity operations. The cognitive shift in analyzing Voyager's plumbing is the realization that the primary operational battle in deep space is not protecting electronics, but preserving the fluid dynamics of a liquid that wants to solidify into rock. Electronics can often survive extreme cold by slowing down or operating at lower voltage thresholds, but a frozen liquid fuel line represents an irreversible mechanical failure point. Voyager's survival requires maintaining an artificial terrestrial thermal microclimate, keeping a narrow network of titanium tubes at a spring-like temperature of 10 to 15 degrees Celsius, while suspended in a vacuum just 3 degrees above absolute zero. As matter drops toward absolute zero, the fundamental physical properties of structural materials undergo profound shifts governed by quantum mechanics and solid-state physics. Materials that are ductile, resilient, and flexible at room temperature can become extremely brittle, fragile, and prone to spontaneous catastrophic failure when exposed to cryogenic temperatures. The structural longevity of Voyager 1 depends on a careful selection of metallic alloys, crystalline insulators, and synthetic polymers chosen specifically for their thermomechanical stability across extreme temperature gradients. When metals cool, their crystalline atomic lattices contract as thermal vibrational energy decreases. This lattice contraction brings constituent atoms closer together, altering interatomic bond potentials and restricting the movement of linear lattice defects known as dislocations. In metals with a body-centered cubic crystal structure, such as carbon steels and low-alloy ferritic metals, cooling below a specific threshold called the ductile to brittle transition temperature causes dislocation motion to freeze entirely. Under these conditions, the metal loses its ability to yield plastically under mechanical stress. Instead of bending or stretching, the material undergoes cleavage fracture, shattering like glass under modest mechanical impacts or thermal stresses. To prevent cryogenic embrittlement, aerospace engineers constructed Voyager 1's primary load-bearing chassis, mounting rings, and structural brackets using alpha-beta titanium alloys, predominantly Ti6Al4V, and high-strength aluminum alloys such as 6061T6 and 7075T6. Aluminum and titanium alloys possess face-centered cubic or hexagonal close-packed crystal structures. In face-centered cubic and hexagonal close-packed metals, dislocation motion remains energetically favorable even as temperatures approach absolute zero, preserving high fracture toughness, impact resistance, and structural ductility across deep cryogenic regimes. However, structural embrittlement is only one aspect of cryogenic materials dynamics. A more insidious hazard in deep space is the coefficient of thermal expansion, mismatch between dissimilar materials joined together within the spacecraft. Every physical material contracts at a unique rate per degree of temperature change. For example, aluminum has a relatively high thermal expansion coefficient of approximately 23 microstrain per Kelvin, whereas titanium contracts at roughly 8.6 microstrain per Kelvin, copper at 16.5, and silicon semiconductors at just 2.6. When two dissimilar materials such as a copper trace bonded to a silicon chip, an aluminum bracket bolted to a titanium strut, or an electronic component soldered to a fiberglass printed circuit board are cooled through a temperature span of over 200 degrees. They attempt to shrink by vastly different physical amounts because the materials are mechanically pinned together at their interfaces. This differential thermal contraction generates immense internal shear stresses. Over decades of deep thermal cooling, these microscopic stresses can cause solder joints to snap, metallic traces to lift off circuit boards, and microscopic cracks to propagate across semiconductor dies, severing electrical continuity without any external physical collision. To protect the decagonal bus and its internal components from uncontrolled radiative heat loss into space, Voyager 1 is wrapped in high-performance multi-layer insulation, or MLI, blankets. MLI blankets do not function like terrestrial fiberglass or ceramic foam insulation, which rely on trapping stagnant air to inhibit thermal conduction and convection. In the high vacuum of space, conductive air insulation is completely non-functional. Instead, MLI is engineered strictly as a high-efficiency infrared radiation shield designed to block photon transfer. An MLI blanket consists of a series of ultra-thin sheets of synthetic polymer film, typically mylar or Kapton, each measuring only a few micrometers in thickness. Every film layer is coated on one or both sides with a microscopic, vapor-deposited film of high-purity aluminum or gold. These metallized surfaces act as highly efficient optical mirrors, possessing an infrared reflectivity exceeding 98%. When infrared thermal photons emitted by the warm spacecraft hull strike the innermost layer of metallized film, the vast majority are reflected straight back toward the interior. Between each reflective layer of film lies a thin spacer layer of coarse Dacron net mesh. The physical function of the mesh spacer is critical. It prevents adjacent metallized film sheets from touching one another. If the reflective sheets came into direct physical contact under compression, heat would conduct rapidly from one sheet to the next through thermal contact resistance, completely short-circuiting the insulation. By using the mesh to maintain uniform vacuum gaps between 20 to 30 individual reflective layers, thermal transfer is forced to occur exclusively through a sequence of photon emission, absorption, and re-reflection across each successive layer, reducing overall radiative heat loss by several orders of magnitude compared to a bare metallic surface. The exterior surface of Voyager 1's main chassis is enclosed in characteristic black Kapton MLI blankets, tailored to form a seamless thermal seal around the decagonal bus. Kapton is selected for exterior layers because of its exceptional chemical resistance, high dielectric strength, and stability under intense ultraviolet and ionizing radiation. The black color results from a carbon-filled outer coating designed to emit static electrical charges that would otherwise accumulate on the spacecraft hull from interactions with space plasma, preventing electrostatic discharge arcs that could damage sensitive microelectronics. Analyzing the solid-state physics of solder joint fatigue under cryogenic thermal cycling illuminates the extreme reliability standards required for Voyager's construction. Printed circuit boards were assembled using eutectic tin-lead solder 63% tin, 37% lead, which possesses a low melting point and high fatigue resistance. However, at temperatures below -50 degrees Celsius, tin undergoes a slow allotropic phase transformation known as tin pest, converting from ductile metallic white alpha tin into brittle, non-metallic grey beta tin. To prevent this phase transformation, lead content was precisely controlled, and trace amounts of antimony were added to stabilize the metallic crystal structure across decades of deep freeze exposure. Additionally, synthetic polymer materials such as fluorinated ethylene propylene and Teflon, used in coaxial cables and wiring insulation, undergo glass transitions at low temperatures. Below their glass transition temperatures, polymer chains lose their ability to slide past one another, transforming flexible cable jackets into rigid, glassy shells. If external articulation mechanisms or thruster booms flexed these embrittled cables, the polymer insulation could crack open, exposing raw copper conductors to short circuits. Engineers avoided dynamic cable flexing in unheated areas, locking wiring harnesses into rigid structural channels. Furthermore, thermal outgassing under vacuum conditions poses a material degradation risk that interacts directly with cryogenic surfaces. In a high vacuum, volatile organic compounds, unreacted solvents, and plasticizers contained within synthetic resins slowly evaporate into space. If warm internal electronics outgas volatile molecules inside the equipment bays, those gaseous molecules can migrate toward cold exterior surfaces such as optical lenses or MLI blanket edges, where they immediately condense and freeze into thin, sticky films. Spacecraft materials were rigorously baked out in thermal vacuum chambers prior to integration to eliminate volatile compounds before launch. The microscopic crystalline physics of polymer degradation at extreme low temperatures also dictated material selection for electrical wire insulation. Standard vinyl or rubber insulation becomes rock hard and extremely brittle below -30 degrees Celsius, cracking under mechanical strain and causing electrical short circuits. Engineers selected specialized Kapton film wraps and fluorinated ethylene propylene coatings for wiring harnesses. These fluoropolymer materials retain atomic flexibility and high dielectric resistance, even when cooled to cryogenic temperatures, preserving electrical insulation integrity across half a century of continuous deep space transit. A detailed evaluation of adhesive bonding agents used throughout the MLI blankets and structural mounts reveals additional cryogenic material considerations. Epoxy resins and silicone adhesives utilized to secure sensor mounts and blanket seams exhibit significant contraction differences relative to their metallic substrates. To absorb microstrains without debonding, engineers formulated flexible, low-outgassing epoxy mixtures impregnated with microscopic glass spheres, providing compliant mechanical buffer layers that prevent catastrophic joint delamination at liquid nitrogen temperatures. The cognitive shift in examining Voyager's material dynamics lies in realizing that a deep space probe does not freeze as a uniform solid block. It exists as a dynamic physical mosaic of competing thermomechanical forces. The primary threat to long-term survival is not merely the low ambient temperature, but the relentless microscopic shear stress generated by differential thermal contraction across millions of material interfaces. Voyager's half-century lifespan is a monument to material selection and joint engineering that accurately anticipated how every alloy, resin, solder joint, and insulating film would shrink and hold together across decades of continuous thermal decay. Every physical body suspended in the vacuum of space exists under the uncompromising governing law of radiative thermal equilibrium. This thermodynamic principle dictates that the rate at which heat energy enters a closed system must equal the rate at which heat energy leaves the system, plus any net change in the thermal energy stored within the system's internal mass. For Voyager 1 drifting in the interstellar void, external solar thermal input is effectively zero. Therefore, the spacecraft's internal thermal balance is defined entirely by internal heat generation, produced by the nuclear decay of the RTGs and the electrical dissipation of internal circuits versus radiative heat loss emitted outward into the cosmic background. This equilibrium condition can be formulated precisely using the Stefan-Boltzmann radiation equation. The total radiant power emitted by the spacecraft into space is proportional to its effective surface emissivity, surface area, and the fourth power of absolute temperature. Because the emitted power scales with the fourth power of absolute temperature, even a minor reduction in internal heat generation requires a corresponding drop in internal temperature to maintain radiative balance. In the early phases of the mission, during the late 1970s and early 1980s, Voyager 1 operated with an abundance of thermal energy. The 3 RTGs were fresh, generating over 4,700 watts of nuclear heat and nearly 470 watts of electrical power. As electrical current flowed through the spacecraft's instruments, computers, and transmitters, resistive dissipation converted this power into internal heat. Combined with the massive thermal plume from the RTGs, the interior of the decagonal bus risked overheating during close flybys of Jupiter and Saturn, which could degrade delicate tape recorders and electronic components. To regulate this variable thermal environment dynamically, spacecraft designers incorporated active mechanical vents, known as thermal louvers, onto the exterior faces of individual equipment bays, mounted directly over cutouts in the aluminum chassis. These louvers resemble miniature metallic window blinds. Each louver blade is constructed from polished, low-emissivity aluminum and is mechanically linked to an internal bimetallic coil spring housed within the equipment bay. A bimetallic spring consists of two thin strips of different metals, typically brass and steel, bonded tightly together face to face. Because the two metals possess different coefficients of thermal expansion, changes in temperature cause the strip to bend or uncoil predictably. As the temperature inside an equipment bay rose, the heat conducted into the bimetallic spring, forcing it to expand and mechanically rotate the louver blades open. Opening the louvers exposed high emissivity black thermal paint applied to the internal chassis plates underneath. This allowed high fluxes of infrared photons to escape freely into space, cooling the compartment. Conversely, as internal temperatures dropped, the bimetallic springs cooled and contracted, driving the louver blades shut. Closed louvers covered the black paint with polished aluminum blades, reflecting internal infrared radiation back into the bay and trapping thermal energy. These thermal louvers provided a completely autonomous, passive mechanical feedback loop that required zero electrical power, zero computer instructions, and zero electronic sensors to operate. They continuously adjusted the spacecraft's effective radiative aperture based purely on the local physical temperature of the underlying structural chassis. For the first 2 decades of the mission, these mechanical blinds opened and closed silently as equipment was turned on and off, stabilizing internal electronics at comfortable operating temperatures between 10 and 30 degrees Celsius. However, as decades passed and Voyager 1 drifted past the outer planets into interstellar space, the energy budget underwent an irreversible structural decline. The nuclear decay of plutonium-238 steadily reduces its thermal output by approximately 0.78% per year. Simultaneously, the silicon-germanium thermocouples inside the RTGs suffer from solid-state material degradation, reducing their electrical conversion efficiency over time. As a result, total electrical power output has plummeted from 470 watts at launch to less than 220 watts today. With vastly less electrical current flowing through internal circuits, internal electrical resistance heating inside the bays dropped precipitously. One by one, the internal equipment bays cooled down. The bimetallic springs contracted fully, driving the thermal louvers completely shut. For more than 2 decades, all thermal louvers on Voyager 1 have remained permanently sealed, locking the spacecraft into its maximum thermal retention configuration. To calculate the exact thermal dissipation of electronic components, engineers utilized the Joule heating law. Every active microchip, relay coil, voltage regulator, and digital logic gate acts as a microheater, converting electrical potential energy directly into atomic lattice vibrations. In an equipment bay consuming 20 watts of electrical power, 20 watts of waste heat is released continuously into the surrounding aluminum chassis. When that equipment is switched off to preserve bus voltage, 20 watts of heating disappears instantly, causing the bay's local thermal balance to decay toward cryogenic equilibrium. Furthermore, internal thermal radiation transfer between adjacent decagonal bays occurs across internal aluminum bulkheads. The 10 equipment bays are arranged in a circular ring around the central hydrazine tank cavity. Bays containing high-power electronics such as the radio transmitter amplifiers in Bay 1 and the main computers in Bay 5 transfer heat laterally through aluminum bulkhead walls into cooler adjacent bays housing low-power science data interfaces. This internal conductive and radiative heat sharing creates a thermal ring bus that mitigates localized freezing, redistributing waste heat across the entire circumference of the spacecraft. Detailed transient thermal modeling illustrates how the spacecraft responds to sudden power mode changes. If the main radio transmitter switches from high power 28 watts RF output to low power mode 12 watts RF output, the reduction in internal waste heat initiates an exponential thermal decay within Bay 1. The local bay temperature drops according to an exponential decay function, governed by the compartment's thermal time constant. The bay takes over 48 hours to settle into its new, lower equilibrium temperature, giving ground controllers time to evaluate telemetry before critical thresholds are breached. The mathematical formulation of internal radiant exchange within the equipment bays involves solving a set of coupled radiative heat balance equations across all 10 bays. Each bay acts as a grey body cavity with defined surface areas, emissivities, and view factors relative to adjacent bulkheads and the central fuel tank. By balancing conductive heat flow through aluminum bulkheads with radiative exchange across interior cavity spaces, thermal software models accurately predicted that Bay 1 radio transmitter and Bay 5 computers would remain the warmest structural zones, providing essential heat sinks for the entire probe. Transient thermal modeling also demonstrates the extraordinary thermal inertia of the central hydrazine tank. Weighing over 100 kilograms when fully fueled, the tank and liquid propellant combination possesses a massive bulk heat capacity. If all internal electrical heating was suddenly cut off, this central fluid mass would act as a thermodynamic reservoir, cooling at a rate of less than 0.1 degrees Celsius per hour. This high thermal inertia provided vital safety margin for flight software fault recovery routines, ensuring that short-term computer resets or power interruptions would not lead to rapid propellant freezing. The cognitive shift in understanding Voyager's energy budget is that electrical power management and thermal management are physically identical operations. Mission managers at NASA's Jet Propulsion Laboratory cannot evaluate power consumption in isolation. Turning off an instrument or transmitter to save electrical current does not merely alter the spacecraft's power margin. It immediately removes a physical heat source from that specific compartment, causing local temperatures to drop toward the cryogenic environment. Every power management decision is simultaneously a thermodynamic calculation that dictates which bay will cool, how fast its temperature will plunge, and whether adjacent propellant lines or solder joints will cross their critical failure limits. When Voyager 1 was designed and constructed in the early 1970s, digital computing was in its infancy. High-density solid-state memory, flash storage, and modern microprocessors did not exist. The spacecraft's command, control, and data handling architecture relies on three separate, redundant dual computer systems: the Computer Command Subsystem (CCS), the Flight Data System (FDS), and the Attitude and Articulation Control Subsystem (AACS). These computers run on custom 18-bit serial processors constructed from discrete logic chips, utilizing magnetic core memory modules with a total storage capacity of just 28 kilobytes, a tiny fraction of the memory required to store a single digital photograph on a modern smartphone. Despite these severe computational constraints, JPL computer scientists embedded within this primitive codebase some of the most sophisticated fault protection, power sharing, and thermal triage algorithms ever deployed in spaceflight history. As available electrical power from the RTGs declined over decades of deep space operations, ground controllers realized that Voyager 1 would eventually reach a critical thermal threshold. Available electrical current would no longer be sufficient to power all scientific instruments, transmitters, and dedicated survival heaters simultaneously. Without intelligent software intervention, the spacecraft would suffer a catastrophic low-voltage brownout, causing its central computers to reset, losing spatial orientation and freezing its instruments solid. To prevent this failure mode, JPL software engineers designed complex algorithmic triage routines to manage power and heat distribution autonomously across interstellar timescales. The flight software continuously monitors system health parameters using analog telemetry sensors distributed throughout the decagonal bus. Temperature sensors, current shunts, and main bus voltage monitors feed continuous real-time data into the computer command subsystem. If main bus voltage drops below a strict safety limit indicating that total electrical demand exceeds the RTG's declining supply, the CCS automatically triggers a high-priority fault protection routine known as PRK power check. Upon activation, PRK executes a rapid, prioritized shutdown sequence, systematically deactivating non-essential electrical loads to stabilize main bus voltage before central processing units brown out. However, shedding an electrical load instantly alters the internal thermal equilibrium of the affected equipment bay. To counter localized freezing caused by instrument shutdowns, the flight software executes precise heat-sharing routines. Engineers discovered that by selectively modifying the operating modes of remaining active systems, they could dynamically redirect internal thermal energy across the aluminum chassis. For example, if a specific science instrument compartment begins cooling toward dangerous levels, controllers can reconfigure the digital telemetry unit or adjust the operational duty cycles of radio transmitter power amplifiers located in adjacent bays. The waste heat generated by these heavily loaded electronic systems conducts through shared aluminum mounting plates, providing a secondary thermal blanket to unpowered components nearby. This software-driven thermal management relies heavily on the physical principle of thermal inertia. Voyager 1 possesses a finite structural thermal mass, the total combined heat capacity of its aluminum chassis, titanium fuel tank, hydrazine propellant, science instruments, and wiring harnesses. Thermal mass acts as a thermodynamic damper, resisting rapid temperature changes. When an electronic heat source is switched off, the local bay temperature does not instantly drop to absolute zero. Instead, it decays along an exponential cooling curve governed by the compartment's thermal time constant. Where resistance is the thermal resistance to space and capacity is the thermal heat capacity of the mass. Flight software algorithms exploit this thermal lag to execute time-phased power cycling routines. By periodically toggling electrical loads between different bays, the software allows components to cool down safely without crossing their critical minimum temperatures before another thermal source is brought online nearby. This creates a dynamic, rolling thermal wave across the spacecraft chassis, maintaining structural warmth while operating well below the total electrical power budget. Deep analysis of the computer command subsystem's execution architecture reveals how magnetic core memory resilience contributes to thermal survival. Unlike modern volatile semiconductor RAM, which loses stored data instantly if supply voltage drops or if temperatures plunge below semiconductor operating limits, magnetic core memory stores binary bits as physical magnetic polarization states in tiny ferrite rings threaded on copper wires. Magnetic polarization is completely non-volatile and unaffected by cryogenic temperatures. If Voyager 1 experiences a temporary thermal brownout that halts processor clock cycles, the software state, memory contents, and fault protection pointers remain perfectly intact in magnetic memory, allowing the computer to resume execution immediately upon power restoration. Furthermore, the Flight software incorporates autonomous gyro management to conserve both electrical power and thermal energy. Voyager 1's mechanical gyroscopes require significant electrical power to spin their heavy rotors at high speeds, generating substantial internal heat but consuming precious RTG current. Software engineers modified the ACS algorithms to operate the probe in a gyro-free stellar tracking mode for extended cruise phases, utilizing optical celestial sensors to maintain orientation. Gyros are spun up only during critical trajectory maneuvers, reducing baseline power demand while managing localized thermal dissipation inside the AACS equipment bay. Software thermal management routines also include automated telemetry polling loops that flag anomalous temperature rates of change. If an analog temperature sensor inside Bay 7 detects a cooling rate exceeding 0.5 degrees Celsius per hour, the CCS does not wait for absolute temperature threshold breaches. Instead, it proactively executes corrective load shifting macros, proving that predictive software logic is essential for survival when round-trip light travel communication times with Earth exceed 44 hours. To handle communication blackout periods during solar conjunctions or ground station handoffs, the CCS software incorporates autonomous macro routines known as sequence event generators. These macro loops allow the computer to autonomously manage thermal survival routines for up to several weeks without ground intervention. If a telemetry sensor fails due to cryogenic degradation, The software cross-references secondary thermal sensors in adjacent bays, utilizing majority voting logic to distinguish between genuine component freezing and sensor telemetry corruption. The implementation of low-level assembly language power monitoring loops inside the CCS processor highlights the seamless integration of software and hardware thermal control. Every 10 seconds, the processor checks the main bus voltage shunt monitor. If voltage margin drops by even a fraction of a volt, the software instantly branches to a power-shedding subroutine that toggles secondary instrument heaters in a pre-programmed sequence. By executing these micro-adjustments continuously, the software stabilizes both electrical bus voltage and structural heat distribution without requiring real-time commands from Earth. The software interface between the flight data system and the telemetry modulation unit demonstrates how data rate scaling protects the thermal budget. When signal-to-noise margins degrade due to extreme distance or thermal drift in RF preamplifiers, the computer automatically steps down telemetry transmission speeds from 1152 bits per second down to 160 and eventually to 16 bits per second. Lower bit rates require less RF power output from the S-band traveling wavetube amplifiers, reducing electrical current draw and preserving power margins while allowing the active amplifier to operate at a cooler, stable thermal equilibrium. Furthermore, autonomous memory scrubbing routines in the CCS mitigate radiation-induced soft errors without triggering full system reboots. Every hour, background software cycles through magnetic core memory addresses, checking parity bits across stored command tables. If a cosmic ray collision flips a bit in a non-critical buffer, the software corrects the memory state silently. This continuous background maintenance prevents false fault triggers that could accidentally shut down active instrument heaters or misalign attitude control thrusters. Examining the hardware interrupt priority architecture within the computer command subsystem shows how emergency power checks take immediate precedence over scientific data processing. The processor architecture includes a nested interrupt controller where main power bus undervoltage signals trigger an unmaskable hardware interrupt level 0. When this interrupt fires, all low-priority telemetry gathering and instrument servicing routines are suspended within a single clock cycle, jumping execution directly to the PWR-CHK subroutine to shed unneeded loads before processor rail voltages degrade. The cognitive shift here reveals that lines of code can function as physical thermal shields. In traditional aerospace engineering, thermal control is accomplished using physical hardware insulating blankets, heat pipes, radiators, and electric resistance heaters. But on Voyager 1, where physical hardware cannot be modified, repaired, or added across billions of kilometers of space, low-level assembly language code functions as a dynamic thermal management system. The software actively manipulates the flow of thermodynamic entropy across the machine, calculating the precise electrical trade-offs required to keep the physical body of the probe warm enough to survive another day in the cosmic void. In August 2012, Voyager 1 achieved one of the most historic milestones in human exploration. It crossed the heliopause and entered interstellar space. This transition marked more than just a symbolic geographic departure from the solar system. It fundamentally altered the external physical environment interacting with the spacecraft's outer surfaces and scientific instruments. For millions of kilometers prior to this boundary, Voyager 1 traversed the helios sheath, the turbulent outer region of the heliosphere, where the solar wind slows down and compresses as it impacts the advancing interstellar medium. In this region, the spacecraft was immersed in a hot, extremely low-density solar wind plasma with kinetic temperatures reaching hundreds of thousands of Kelvin. While this temperature sounds intense, the particle density was far too low to transfer meaningful conductive heat to the probe. However, the solar wind magnetic field provided an essential shield, deflecting low-energy galactic cosmic rays away from the inner solar system. When Voyager 1 crossed the heliopause, this solar magnetic shield vanished, The spacecraft stepped directly into the local interstellar cloud, an environment with radically different plasma and radiation characteristics. Plasma density increased instantly by more than an order of magnitude, jumping from roughly 0.002 particles per cubic centimeter inside the heliosphere to over 0.08 particles per cubic centimeter outside. Simultaneously, the ambient kinetic plasma temperature dropped sharply, transitioning from hot solar ions to the cooler, denser gas of the interstellar medium. This environmental shift introduced subtle but significant thermal and electrical effects on the spacecraft's exposed surfaces and scientific sensors. The increased plasma density altered the electrostatic charging environment of Voyager 1's exterior hull. Suspended in space, a probe continuously accumulates an electrostatic charge from interactions with ambient ions, electrons, and solar ultraviolet photons. Outside the heliopause, the higher flux of cold interstellar ions shifted the spacecraft's equilibrium floating potential, altering how low-energy charged particles interact with the hull and sensor apertures. Furthermore, the flux of high-energy galactic cosmic rays energetic atomic nuclei accelerated to near light speed by distant supernova explosions increased dramatically outside the protective solar bubble. These ultra-high energy particles easily penetrate the spacecraft's outer insulation blankets and aluminum skin, striking silicon semiconductor microchips and sensitive scientific detectors. When a cosmic ray passes through a semiconductor lattice, it deposits energy along its ionization track, a phenomenon known as a single-event upset. This sudden energy deposition generates localized microscopic thermal spikes. Nanometer-scale heat bursts within the silicon crystal that can corrupt memory registers, flip digital bits, or trigger transient electrical currents. Voyager 1's central computers and instrument processing units had to rely on internal error detection routines and redundant circuit architectures to filter out these radiation-induced thermal and electrical disruptions. To continue operating scientific instruments like the cosmic ray subsystem, the low-energy charged particle detector, and the magnetometer in this unshielded environment, Voyager 1 had to maintain strict thermal calibration. Electronic sensors rely on precise reference voltages and low-noise operational amplifiers to measure incoming interstellar ions and magnetic fields. As internal temperatures continued to decay following the heliopause crossing, sensor amplifier gains and thermal noise baselines drifted predictably. Ground scientists at JPL had to continuously update their data interpretation software to compensate for the physical cooling of the detectors, mathematically separating true interstellar scientific signals from the thermal noise drift of freezing electronics. Examining the plasma wave science instrument reveals how environmental thermal shifts directly impacted scientific data collection. The plasma wave science instrument utilizes two 10-meter-long flexible beryllium copper antenna rods extending outward from the spacecraft bus to measure plasma oscillations. In interstellar space, these long antenna booms radiate heat directly into space, cooling to extreme cryogenic temperatures. Because electrical resistivity in metals decreases as temperature drops due to reduced electron-phonon scattering, the cold beryllium copper antenna rods actually experienced a slight decrease in internal electrical resistance. This improved their sensitivity to high-frequency electric field oscillations, allowing the instrument to detect subtle interstellar plasma density oscillations triggered by solar coronal mass ejection shock waves penetrating the heliopause. Furthermore, the magnetometer instrument mounted on a long 10-meter fiberglass boom required extreme thermal stability to measure ultra-weak interstellar magnetic fields measured in fractions of a nanotesla. The magnetometer sensors utilize flux gate cores that are highly sensitive to thermal drift. To prevent temperature changes from corrupting magnetic field readings, the fluxgate sensors were wrapped in dedicated MLI blankets and equipped with specialized low-power heaters, keeping sensor temperatures within a strict calibration window even as the boom supporting them cooled toward 3 Kelvin. The thermal interaction of interstellar dust grains striking the spacecraft skin also provides a fascinating physical study. As Voyager 1 moves through the local interstellar cloud at 17 kilometers per second, microscopic dust grains collide with the high-gain antenna reflector. Each hypervelocity impact vaporizes the dust grain and a tiny speck of surface metal, creating a microscopic plasma plume that expands rapidly. The energy thermalization of these impacts generates miniature radio frequency transients detected by the plasma wave science antennas, allowing scientists to calculate interstellar dust density while monitoring antenna thermal integrity. In addition, cosmic ray ionization of the outer Kapton insulation layers alters the dielectric constant of the insulating films over decades. High-energy protons breaking chemical bonds within the polyimide matrix generate microscopic carbonaceous defects, slightly increasing the blanket's far-infrared emissivity over 40-year timescales. Spacecraft thermal analysts had to factor this radiation-induced emissivity creep into their long-term thermal loss projections to maintain accurate bay temperature forecasts. Analyzing the thermal dynamics of the low-energy charged particle LECP stepper motor reveals how mechanical friction behaves in interstellar cryogenic regimes. The LECP detector uses a motor-driven rotating platform to sweep its sensor aperture across 360 degrees. In the cold vacuum outside the heliopause, conventional liquid lubricants would freeze into solid wax, jamming the gear teeth. Engineers utilize dry film molybdenum, disulfide lubricants, and precise thermal heater pulses to maintain motor rotation, allowing the instrument to sample interstellar ion directions across decades of flight. Furthermore, cosmic ray spallation within the spacecraft's structural titanium generates trace secondary particle showers that interact with nearby sensor electronics. When ultra-high-energy galactic protons collide with heavy titanium nuclei in the chassis frame, they eject secondary neutrons and pions. Instrument shielding and digital event discrimination logic were designed to filter out these secondary structural particle bursts, ensuring that CRS and LECP scientific telemetry records pristine interstellar cosmic ray fluxes rather than spacecraft self-induced background radiation. The cognitive shift in analyzing the heliopause crossing is that the boundary of the solar system represents a thermodynamic phase transition for deep space science. Leaving the Sun's magnetic bubble exposed Voyager 1 to a colder, harsher cosmic environment, requiring its aging systems to maintain internal thermal stability while pelting through the unfiltered particle flux of interstellar space. While the nuclear decay of plutonium-238 follows an immutable half-life curve dictated by quantum mechanics, the decline of Voyager 1's electrical power is accelerated by a second, equally critical physical phenomenon, the physical degradation of its solid-state semiconductor thermocouples. Understanding this dual decay process explains why the spacecraft loses electrical power significantly faster than its nuclear fuel decays, driving the ongoing thermal crisis on board the probe. The silicon-germanium unicouples inside the three RTGs operate in an exceptionally harsh thermomechanical environment. The hot junction of each thermocouple is exposed to continuous temperatures near 1000 degrees Celsius, positioned just centimeters away from the glowing plutonium core, while the cold junction is thermally bonded to radiator fins exposed to the absolute cold of space. This extreme temperature differential generates intense thermal stress across the semiconductor material continuously for nearly 50 years. Over decades of uninterrupted operation, several microscopic solid-state degradation mechanisms occur within the silicon-germanium material. First, at operating temperatures of 1000 degrees Celsius, silicon and germanium atoms within the crystal lattice undergo slow, continuous sublimation and physical migration. Atoms slowly vaporize from the hot end of the unicouple leg and redeposit on cooler structural surfaces nearby. Over time, this material transport thins the cross-sectional area of the thermocouple legs, increasing their internal electrical resistance while reducing their structural load capacity. Second, the dopant atoms added to the silicon-germanium lattice to create p-type and n-type semiconductor properties. Typically phosphorus and boron undergo thermal diffusion. Driven by high temperatures across decades, these dopants slowly diffuse out of their optimized concentration profiles within the semiconductor matrix. As dopant distribution flattens, the material's Seebeck coefficient degrades, reducing its ability to convert a given thermal gradient into electrical voltage potential. Third, continuous exposure to low-level neutron radiation produced by spontaneous fission events within the plutonium fuel creates lattice defects within the silicon-germanium crystals. These radiation-induced vacancies and dislocations act as scattering centers for charge carriers, electrons and holes and thermal phonons, increasing electrical resistivity while altering the material's internal thermal conductivity. As a combined result of these physical degradation channels, the electrical output of the RTGs decays at a rate of approximately 1.6 to 2% per year, more than double the natural 0.78% annual decay rate of the plutonium-238 radioisotope alone. At launch in 1977, the three RTGs produced roughly 470 watts of usable electrical energy from nearly 5,000 watts of thermal heat. Today, that electrical yield has fallen below 220 watts, while total thermal output has dropped to approximately 2,600 watts. This continuous loss of electrical power creates a compounding thermal loss loop inside the spacecraft chassis. Less electrical current generated by the RTGs means less electrical power available to operate onboard electronics, as instruments, heaters, and transmitter modes are powered down or throttled to preserve main bus voltage. Internal electrical resistance heating decreases dramatically. The spacecraft loses the electrical waste heat that previously buffered its internal bays against the cold environment. Mathematical modeling of thermocouple degradation shows that electrical power output decays according to a dual exponential function combining nuclear thermal decay and solid-state degradation over time. The decay rate accelerates slightly as internal electrical resistance increases, generating internal resistive losses within the unicouple legs themselves. Furthermore, thermal contact resistance between the cold junctions of the thermocouples and the outer aluminum radiator fins increases over time. Differential thermal expansion cycling between the silicon-germanium legs and the radiator mounting plates induces microgaps at the bond interface. These microgaps inhibit conductive heat transfer to the radiator fins, causing the cold junction temperature to rise slightly. According to the Seebeck equation, any increase in cold junction temperature shrinks the temperature differential across the thermocouple, directly reducing electrical voltage generation. This power decline forced mission engineers to monitor the spacecraft's shunt regulator system with extreme precision. The shunt regulator acts as an electrical safety valve, dissipating excess RTG power as heat through external resistor bars when total power generation exceeds spacecraft demand. In the early decades of flight, the shunt regulator continuously dumped tens of watts of excess power into space. Today, the shunt regulator operates near zero margin. Virtually every single watt of electrical current produced by the degrading thermocouples is consumed directly by active spacecraft loads. Examining the mechanical load distribution across the RTG mounting boom reveals secondary structural effects of thermocouple aging. As silicon-germanium material sublimates from the unicouples, the mechanical cross-section of each leg shrinks by up to 15%. While spacecraft acceleration forces are near zero in interstellar cruise, tiny impulse torques from thruster firings transmit shear loads through the RTG housing. Engineers performed structural integrity checks to verify that embrittled, thinned thermocouple legs could still withstand thruster shock loads without fracturing. Solid-state physics modeling of thermoelectric unicouple degradation also accounts for thermal bypass losses, as the reflective insulation wraps surrounding the unicouple legs degrade over decades. A larger fraction of core nuclear heat bypasses the semiconductor legs entirely, radiating directly into the outer RTG casing. This parasitic thermal leakage reduces the heat flux passing through the thermocouple legs, further diminishing electrical power output. Solid-state modeling of dopant atom precipitation within the silicon-germanium lattice reveals additional microstructural power decay channels. Under prolonged exposure to high operating temperatures, phosphorus and boron dopant atoms slowly aggregate into electrically inactive clusters along crystal grain boundaries. This precipitation reduces the effective carrier concentration within the semiconductor legs, lowering electrical conductivity while increasing internal resistive losses within the unicouple itself. Detailed mathematical modeling of Seebeck coefficient temperature dependence underscores the nonlinear voltage decay experienced by the RTG array. The Seebeck coefficient of silicon germanium varies dynamically as a function of local lattice temperature. As core nuclear thermal output decays and hot junction temperatures drop from 1000 degrees Celsius down to 900 degrees Celsius, the material's thermal voltage generation drops faster than a simple linear extrapolation would predict, compounding the electrical power loss. The cognitive shift lies in recognizing that Voyager's power loss is not just a chemical or nuclear depletion, but a solid-state aging process occurring at the atomic scale. The nuclear core remains hot, emitting thousands of watts of raw thermal energy. But the microscopic atomic engine designed to harvest that heat into electricity is slowly crumbling from decades of intense thermal stress and radiation damage. Voyager 1 is slowly starving of electrical current even while its nuclear heart remains hot enough to melt lead. Facing a relentless decline in electrical power and an inevitable drop in internal temperatures, flight controllers at NASA's Jet Propulsion Laboratory were forced to implement a radical operational strategy known as the Interstellar Energy Management Plan. This strategy represents a deliberate, calculated campaign of scientific triage systematically turning off subsystems, science instruments, and structural heaters to extend the operational life of the spacecraft for as long as physically possible. Beginning in the late 1990s and accelerating through the 2000s, controllers issued commands to deactivate non-essential hardware. The spacecraft's scan platform, which held the optical cameras that captured the iconic pale blue dot photograph of Earth in 1990, was powered down completely, along with its dedicated survival heaters, the photopolarimeter, the infrared interferometer spectrometer, and the ultraviolet spectrometer were turned off one by one as their planetary flyby missions concluded and power margins tightened. However, the most critical phase of the energy management plan involved intentionally turning off the operational survival heaters dedicated to individual scientific instruments that were still actively gathering interstellar data. Ground testing conducted in the 1970s had established strict thermal design limits for every instrument on board Voyager 1. Components were certified to operate down to specific lower temperature thresholds, typically around -10 to -20 degrees Celsius. Standard engineering protocols dictated that if an instrument's temperature dropped below its certified limit, its internal electronics would fail, circuit traces would snap, and data collection would cease permanently. In a series of high-stakes engineering decisions, JPL mission managers chose to disable the survival heaters on active instruments, including the cosmic ray subsystem, the low-energy charged particle detector, and the magnetometer. The result was an unprecedented real-world experiment in extreme cold material survival. When the heaters were switched off, instrument temperatures plummeted past their official design limits, dropping to -30, -40, and eventually below -60 degrees Celsius, far colder than any thermal chamber test ever conducted prior to launch. Against all predictions of late 20th century aerospace theory, the instruments did not fail. The electronic circuits, solid-state detectors, and operational preamplifiers continued to function with remarkable stability. The silicon semiconductors, solder joints, and wiring harnesses defied expected embrittlement and thermal stress failure, continuing to collect and transmit interstellar particle data at temperatures far below their certified operational limits. This extraordinary endurance is explained by several physical factors operating in deep space. In the absolute vacuum of space, the complete absence of atmospheric moisture means there is zero water condensation or frost formation to short-circuit freezing electronics. Furthermore, because the thermal drop occurred extremely slowly over weeks as heat radiated away into space, differential thermal contraction across circuit board materials occurred gradually, allowing mechanical strain to distribute evenly without inducing sudden shock fractures. Surprisingly, cryogenic cooling actually improved the electronic performance of certain preamplifiers by reducing internal thermal noise, enhancing sensor sensitivity. Analyzing the thermal physics of low-noise field effect transistors inside the instrument preamplifiers reveals why cryogenic temperatures enhance signal processing. Thermal noise generated inside an electrical conductor is proportional to absolute temperature. As an instrument's operating temperature plunged from 260 Kelvin down to 200 Kelvin, thermal voltage fluctuations inside its front-end amplifier circuits dropped by over 20%. This reduction in noise allowed the instruments to resolve extremely weak particle fluxes and magnetic variations in interstellar space that would have been obscured by thermal noise at higher temperatures. Furthermore, mission controllers executed clever operational workarounds to manage thruster-line temperatures without active heaters. In 2017, after 40 years of continuous use, the primary attitude control thrusters on Voyager 1 began showing signs of degradation. Their internal propellant valves required increased firing pulses to operate as silica's deposits accumulated inside fuel orifices. Controllers successfully commanded the spacecraft to switch to a backup set of trajectory correction maneuver thrusters that had been dormant since 1980. Because the trajectory correction maneuver thrusters had remained unheated and unused for 37 years, engineers had to execute a delicate thermal preheating sequence, selectively redirecting electrical current to ensure the long dormant thruster valves and titanium propellant lines reached operational temperature before fuel pressure was applied. The backup thrusters fired perfectly, extending attitude control capabilities by several additional years. In late 2023, when a corrupted memory chip in the flight data system caused Voyager 1 to transmit gibberish telemetry, engineers faced another thermal computational challenge. To isolate the fault without diagnostic tools, they analyzed raw memory dumps transmitted across 24 billion kilometers. They devised a software patch that split the affected code block into small fragments, distributing them across uncorrupted locations in memory. The patch was uploaded successfully in April 2024, restoring structured science telemetry while maintaining the spacecraft's delicate thermal and electrical balance. The operational decision matrix for turning off instrument heaters required complex probabilistic risk modeling. Engineers developed thermal decay simulation software to predict the exact temperature trajectory of each bay following a heater shutdown. By balancing the risk of component embrittlement against the certainty of electrical starvation, controllers established a prioritized shutdown schedule that maximized interstellar science return while extending spacecraft lifespan by more than a decade. The execution of the thruster preheating sequence prior to switching attitude control thruster branches in 2017 highlights the extreme operational precision required by JPL controllers. Because the backup trajectory correction maneuver thrusters had sat unheated at minus 40 degrees Celsius for 37 years, applying sudden hydrazine pressure would have caused thermal shock and propellant line rupture. Controllers commanded localized electrical heater pulses over several days, slowly raising thruster valve temperatures to plus 15 degrees Celsius before executing the first alignment pulse. Furthermore, long-term trend analysis of analog engineering telemetry allowed controllers to build predictive thermal models for unheated instrument bays. By tracking microkelvin temperature decay rates across seasons of interstellar cruise, software algorithms projected exact dates when individual component bays would approach critical phase change boundaries. enabling mission managers to plan power-shedding steps years in advance of potential hardware failures. Evaluating telemetry passing during FDS buffer reorganization demonstrates how software agility preserves data integrity during cold operation. By reindexing data pointer arrays across remaining intact core memory blocks, engineers created a resilient memory buffer that operated continuously at -40 degrees Celsius, proving that software adaptability could overcome physical semiconductor degradation across deep space distances. The cognitive shift in evaluating this cold shutoff strategy is that engineering limits are often conservative operational boundaries, not absolute physical walls. Voyager 1 proved that well-engineered, solid-state electronic systems operating in a dry vacuum can survive thermal regimes far more brutal than their human creators ever dared to specify. By pushing the spacecraft past its official thermal design limits, JPL engineers turned extreme cold from a fatal hazard into an operational baseline, allowing Voyager 1 to continue transmitting interstellar science decades after it was expected to freeze into silence. Despite every algorithmic innovation, materials breakthrough, and high-stakes operational strategy, Voyager 1 moves toward an absolute thermodynamic boundary. The laws of nuclear physics cannot be altered by software updates or ground commands. Within the next several years, by the late 1920s or early 1930s, the electrical output from the RTGs will fall below the absolute minimum threshold required to operate the central computer command subsystem and the main S-band radio transmitter, which requires roughly 50 watts of power to send signals across interstellar distances. When that threshold is breached, Voyager 1 will execute its final automated routine. The central computer will no longer have sufficient electrical current to modulate data, drive the transmitter, or fire the attitude control thrusters. The radio signal that has pulsed continuously across the cosmic void since 1977 will fade and disappear forever. Earth will receive its final bit of telemetry, and Voyager 1 will become an unpowered, silent object drifting through the galaxy. In the immediate aftermath of electrical death, the spacecraft's internal thermal dynamics will enter their final phase transition. Without electrical resistance heating from active circuits, the remaining internal compartments will undergo an irreversible thermal decay. Over weeks and months, the decagonal bus, the titanium hydrazine tank, the science instruments, and the structural struts will radiate their residual thermal energy into the interstellar vacuum. The temperature of the spacecraft will plunge downward, passing through the freezing points of all remaining trace elements, eventually settling into absolute thermal equilibrium with the local interstellar cloud at approximately 2.7 Kelvin. The liquid hydrazine remaining in the fuel lines will freeze solid, locked permanently inside its titanium pipes. The solid-state microchips will cool to within 3 degrees of absolute zero, their atomic lattices coming to a complete thermal standstill. Yet, in a profound cosmic irony, this absolute deep freeze will become the ultimate preservation mechanism for the spacecraft. On Earth, metal structures deteriorate rapidly through oxidation, atmospheric erosion, moisture, wind, and geological activity. In interstellar space, thousands of light years from the nearest star, none of these destructive mechanisms exist. There is no atmospheric oxygen to corrode the aluminum bus, no water vapor to induce rust, no chemical weathering to degrade polymers, and no atmospheric drag to slow the probe's trajectory. At 2.7 Kelvin, chemical reactions effectively cease to occur. The diffusion of atoms within solid metals drops to absolute zero. The crystalline lattices of the aluminum frame, titanium fuel tanks, and beryllium struts become permanently locked in state. Radiation damage from sparse cosmic rays will slowly accumulate across millions of years, but the structural form of the spacecraft will remain intact, floating through an ultra-pure cryogenic vacuum. Mounted to the exterior of Voyager 1's chassis is the Golden Record, a 12-inch gold-plated copper phonograph disc enclosed in a protective aluminum jacket, carrying the sounds, images, and greetings of Earth in the cryogenic vacuum of deep space. This record will survive for hundreds of millions, perhaps billions of years, long after our sun has evolved into a red giant and collapsed into a white dwarf, long after the mountains on Earth have eroded to dust. Voyager 1 will continue to coast silently through the Milky Way, an unyielding monument of cold metal and gold. To project Voyager 1's long-term galactic trajectory across deep time, consider its physical path through the Milky Way galaxy. Operating under Keplerian orbital mechanics around the galactic center, the spacecraft travels at a hyperbolic escape velocity of approximately 16.9 kilometers per second relative to the Sun. In roughly 40,000 years, Voyager 1 will pass within 1.6 light-years of the red dwarf star AC + 7938 in the constellation Camelopardalis. In roughly 300,000 years, it will enter the vicinity of Sirius, the brightest star in Earth's night sky. As it orbits the center of the galaxy every 220 million years, cosmic dust grain impacts will slowly ablate the exterior gold coating of the phonograph record at a rate of less than a few nanometers per million years. The etched audio grooves containing human voices, whale songs, and classical symphonies are protected inside the aluminum cover, preserved in cryogenic dark. The probe will survive multiple galactic rotations, outlasting human civilization, outlasting Earth's biosphere, and continuing to drift through space as a permanent physical artifact of 20th century science. The physical preservation of semiconductor logic gates under deep cryogenic storage also presents a fascinating solid-state reality. Even though electrical current will no longer flow through the silicon chips, the microscopic PN junctions, aluminum interconnect traces, and magnetic ferrite cores will remain physically intact. If a future spacefaring intelligence were to intercept Voyager 1 millions of years from now and provide external electrical power and thermal warmth, the primitive logic circuits of 1977 could theoretically reawaken, ready to process commands once again. Reflecting on the thermodynamic destiny of Voyager 1 connects human engineering to the grand arc of cosmic entropy. The probe was forged in the warm fires of terrestrial industry, powered by the nuclear decay of artificial elements and guided across billions of kilometers by human ingenuity as its internal nuclear heart slowly cools toward absolute zero. Voyager 1 does not disappear. It becomes a permanent part of the interstellar landscape, carrying the memory of Earth into the deep cosmic freeze. The ultimate fate of Voyager 1's metallic components across cosmic timescales involves slow atomic diffusion and micrometeorite erosion. Over hundreds of millions of years, sparse interstellar dust grain hypervelocity impacts will erode the outer aluminum skin at a rate of less than 1 micrometer per million years. The interior decagonal chassis, protected beneath multilayer insulation blankets, and the parabolic antenna dish will remain intact, floating through galactic orbits as a pristine physical time capsule of 20th century human technology. Evaluating hypervelocity interstellar micrometeoroid erosion kinetics confirms that even over billion-year time horizons, structural integrity remains virtually uncompromised. With an interstellar dust flux of fewer than 10 to the power of -15 grains per square meter per second, kinetic sputtering removes material at a microscopic rate, ensuring the main chassis structure preserves its physical geometry as it orbits the galactic core. Finally, the philosophical and scientific legacy of Voyager 1's thermal survival highlights the triumph of human foresight over hostile cosmic physics. By mastering radiation thermodynamics, solid-state nuclear power conversion, cryogenic materials science, and resilient fault protection flight software, human engineers created a machine capable of surviving the absolute cold of deep space, an enduring ambassador of Earth, drifting forever among the stars. The final cognitive shift is the realization that the cold of deep space is not Voyager's ultimate enemy, but its ultimate preserver. The absolute zero environment that ultimately kills the electronic brain of the machine is the exact same environment that guarantees its physical immortality. The cold strips away its voice, its power, and its operational life. But in return, it grants the spacecraft passage across geological time. Voyager 1 survived the cold to teach us about the edge of our solar system, and in the end, the cold will preserve Voyager 1 as an eternal relic of human curiosity drifting among the stars,